Well, welcome everyone to Codesmith, JavaScript, the hard parts, closure. I am Clinks, Michael Clinks Scales. There's far too many Michaels in the world. Going by Clinks is far easier to remember. I'm sure you've known thousands of Michaels in your life, so this is my way of standing out a little bit more there. But I'm one of the engineering instructors here at Codesmith. I am a flex engineering instructor, which just means that I am campus agnostic. I bounce around the various programs, delivering lectures, offering support where needed, and of course, delivering workshops like this one here. Like I said in a little bit of intro here, before Codesmith and really before software engineering, I was walking natural gas pipelines, looking for gas leaks, issues with pipelines. Maybe they weren't painted well enough. I had to note that down as well. But even I got my bachelor's degree in psychology. So it has been a whirlwind sort of venture to end up here. Tonight, we are going to be talking about closure in particular. Closure is one of the most esoteric of JavaScript concepts. This is what enables us to use some very powerful functions like once and memoize, right? In video games, how awful would it be if you could just continuously open up a chest and it would always give you the same super valuable item? That would be terrible. We want that to only happen once, and part of allowing that to happen and making sure that that only happens once is using functions like once, which rely on closure. Memoize in the same way, making sure that our functions are aware of the previous calls that have been made to them. We'll talk more about functions here in a second if that is not clicking. And a lot of our JavaScript design patterns revolve around utilizing modules. These modules demonstrate closure pretty perfectly. Okay. We get into the node section of the course and start working with Node Package Manager and the modules that are there. You'll see a lot of closure. Okay. Additionally, they assist us in building iterators and allow us to maintain our state in an asynchronous world. Okay. Now, with any hard parts, we do want to start and make sure that we have a good understanding of the fundamentals that we're going to be dealing with so that we can get into those hard parts as we get later on in our lecture here. So, functions. We rarely want to just run a piece of code just once, right? We want to define out a blueprint that is going to allow us to reutilize that piece of code again and again and again with different inputs, different parameters, different arguments that have been provided to them. Okay. So here we see a function noted by that function, right? Multiply by 2. That's our function label here. Okay. And then our function definition. Everything following that label. Okay. This label is how we refer to this definition, how we're able to find this definition in our memory there. Okay. Now, in order for us to utilize these functions and to make our way through our code, we have to follow our thread of execution, or as one of my favorite fellow instructors calls it, the toe. Everybody needs a toe. And then in order for us to work with these functions and not just utilize their code blocks once, right? We've got to be able to save that into our memory, whether it be global, local, right? This is within our variable environment. Okay. Let's take a look at this code snippet, and I'm going to ask for a volunteer to get us started. And get a volunteer and help us walk through what is taking place in our first bit of code here. Can we see the snippet down there at the bottom left? Blow it up a little bit if need. Yes, Odin.
I was just volunteering if no one else wants to do it.
Perfect.
Okay. So if I'm reading it right, so the first line of code we have, we're going in our global memory, we're going to declare a variable num and assign it to the value free.
Absolutely.
On our call stack, we're going to add global, which I think we just need to label it, right? Yeah, okay. And then we're going to, after that, we're going to declare a function multiply by 2 and assign it to the function definition.
Okay. So that first line declared our variable, declared that label num, set it equal to the value of 3. And now we've got multiply by 2, which we will set equal to that function definition that is going to follow here. Okay, and what is all contained in that function definition, Odin?
Everything after the parameter input number, so constant result and return result.
Yeah, so everything that we've got here, part of our function definition.
Does the function definition also include the parameter?
Yes.
Okay, it does. Okay.
Yeah, helpful to think about it that way.
Oh, cool. Awesome. Okay. Do you want me to keep going?
Yeah, absolutely.
And then we're going to declare a constant output and assign it to the invocation of multiply by 2 with the parameter num.
Awesome. So we've got a new constant output, and we're setting it equal to, well, we don't know yet, right?
Yeah. It's undefined right now, right?
It's undefined right now because
Okay.
we haven't yet figured out what that value is. But you're right. We're setting it equal to the evaluated
result.
Okay. Invoking multiply by 2 provided num. So what happens next? What happens when we do see that invocation?
We're gonna push onto the call stack multiply by 2 and open a new local execution context.
Absolutely. And let me grab a sticker here so I don't have to draw the whole box.
Sounds good.
Okay. Absolutely right. We have opened up a local execution context here. Okay. As we've been moving here, just one second, sorry.
Okay, my bad.
So we've been working through our thread of execution, making our way down here, right? We found our function definition. Because we haven't invoked it yet, we continue moving. We find that output, set it equal to what is going to be the evaluated result of invoking multiply by 2 provided num here. And now that we have invoked this is where we move into, as Odin has said, our local, holy cow, execution context. And what do you think I have in this box over here, Odin?
The toe, the thread of execution.
Oh, you can't see my pen. What do you think?
Oh, that one. Sorry, that's local memory.
This is my local memory.
Okay.
Absolutely. Okay. So we're starting to see a little bit of inception here. Right, we've got our global execution context. Now we've opened up a local execution context, right? Mm-hmm. Specific to this invocation of multiply by 2 provided num. If you ever need to ask me what I have just written, please do. I understand that I type all day and therefore my handwriting is not that great. Keep us going, Odin.
So then we're going to pair our arguments and our parameters. So we're going to put num is assigned to 3. Is that what we write? Or would we write input number is assigned to 3?
What do you think?
I feel like input number because that's the parameter, right?
Right.
Oh, okay.
So my input number, I will assign the value of 3, pulling that from our num there. Can someone tell me what that's called when we just provide that 3 there, right? Are we still looking at num or are we just looking at the value 3? And Odin, you can pop in on this too if you'd like.
I feel like we're just storing it. Is that what it is? Like, is our local memory for if we need it as of right now? Is that what you're looking for?
Yeah. Is that 3 still attached to num right now? Or is that just a value?
I think it is in the global memory, but as of right now, it's the 3 in our. So right now it's assigned 3 in the num and the input number?
Yes.
Okay.
The thing about primitive data types is that we pass them by value rather than by reference. That's what I'm trying to.
Okay, cool. Awesome. Do you want me to keep going?
Keep it going.
Okay. So Then we're going to, in our local memory, declare a constant result and assign it to the input number, which is free, times 2,
Awesome.
which is going to be 6.
And yeah, we'll skip ahead there.
Okay.
What we're doing, of course, within here is getting that input times 2. That occurs within our local execution context. As we might know, 3 times 2 is 6. We get our result, set that equal to 6. What happens next?
So then we're going to pop our call stack, multiply by 2, and return result to where we needed it in output. So we're going to assign output to 6.
We're going to return that 6. And you're right, we are going to pop this off of our call stack here, right, as we finish that up.
And we're garbage collecting the, what's it called?
Yes, we
local
are.
memory.
We are garbage.
Local execution, okay.
Yes. So we're prepping this for garbage collection. And Odin, what does that mean when we're prepping something for garbage collection?
We're no longer using it, so we're getting off the code. Like we're going back to our global stack frame.
Absolutely. Yeah. So
there's probably a better way of saying that.
We're getting it ready because we're not going to utilize it anymore. We're putting it out by the curb so that JavaScript, our engine, can get ready and toss that out. So we don't have to have that hanging out in our memory. Yes. So then where does our thread of execution head back to?
To the global thread of execution, and we're going to look for where the result's going, and it's going to go to output. So we're going to say output is assigned to 6.
Yes, it is. Awesome. Very near the end here. What happens next?
So I think we're done with our line of code for the declared constant output. So we're going to go to our next line and do declare new output and assign it to the invocation. The evaluated result of multiply by 2 with the argument 10.
Absolutely. I got ahead of myself. So new output set equal to, we don't know yet.
Yeah, undefined, okay.
And then absolutely with that new invocation, and I'll make this a bit smaller here so we can see it, we're opening up a new local execution context here. Let me switch my color. There we go. Okay. So we moved into a new local execution context. New LEC. And with that, we have a new set of local memory within here. Now, because we've opened up this new local execution context, what does that mean, Odin?
It means we've added a stack frame, which is going to be multiplied by 2 again.
Absolutely. So we've added a new stack frame. We've pushed that onto here. When we talk about adding something to a stack, we push and
we push.
Yeah.
There you go. Do you want me to keep going?
Yeah, we'll finish this up.
Cool. Okay, so we need to pair our arguments and parameters. So this time input number is going to be assigned to 10.
Absolutely.
And then we're going to declare a constant result and assign it to input number 10 times 2. So it's going to be 20. And then we're going to return our result, which will garbage collect this local execution context and pop off the stack frame multiplied by 2. And then our new output will be assigned to the evaluated result, which was 20, I believe.
Perfect.
Thank
you so much, Odin. So we walked through all of our thread of execution here. We get to the end. We've assigned values, right, to our output and to our new output from that evaluated result from running that multiply by 2, provided num, and then provided 10, right? I guess I got one step left for you, Odin. What happens at the end here?
Let's see what we have left. So based on the code, I think we answer everything. So let's see. So we already garbage collected both of our local execution context, right? So we have all our values. Is there anything else to do? Am I missing? Sorry, I'm not sure.
It's very related to what we've done in these local execution contexts.
Do we also garbage collect the global execution? Really? Okay, cool.
Because we're all finished up.
Okay.
We're not telling ourselves to do anything else with that. And so when we get done, we garbage collect everything, finish off. We're not importing these results anywhere else, right? We don't need to hold on to that in our memory. Imagine every time you ran a JavaScript file, it just kept stacking up in your memory the results that were provided at the end of that. Yeah.
Got it. Okay. Very cool. Thank you.
Yeah. Thanks so much, Odin. Yes, quick question, Faye.
I noticed that the number 3 is outside of the function scope, right? If we reassign num, like let num equals 4 after the function, but before the const output. So when we call the output, what num does it use? The number 3 or number 4?
So you're saying right here, is that right?
Yeah, we reassign it. First line we have number num 3. Then after the function multiplied by 2, we reassign num equals 4. So when we call output, which number does it use? Number 4 or number 3?
What do you think? What do you think?
Feel like it should use number 4.
Yeah, absolutely. Because when we run this let num equal 4, what's going to happen is, ignore that I've X'd this out already. What's going to happen is num is going to be reassigned to 4 before we ever get to evaluating the result of calling multiply by 2 on num. And so if we're following our thread of execution here, before we ever call upon multiply by 2, right, num has been set to 4. And so then in that case, we would get 8 instead.
I see.
Yeah. So what this, yeah, absolutely. What this is doing here, oh, come on. What this is doing here is placing a label on this definition so that when we reference it later, we know where to look. This multiply by 2 label is creating sort of an address in memory that we can rely upon, okay? And so then whatever num is, whatever the value of num is, when it is eventually called upon is what matters, not what num is when we are defining this multiply by 2 function here. Awesome. Any other questions from our first example here? We'll keep moving. Cool. All right. So we followed our thread of execution through defining a function, calling upon that function a couple times, right? Changing what we were providing as parameters. But what's awesome is that functions can also have multiple labels, multiple names here. So we see in this example, right? Got a label, still multiply by 2, followed by the definition associated with that label, right? We call upon multiply by 2 with that 9, right? Find out the evaluated result. I expect it might be 18. And then we also create a new label and point it at the existing label. Point it at the existing label. Okay. I talked a little bit about pass by value as it related to that 3, right? Numbers are what are called primitive types. Okay, so it was a different 3 that was provided. It was copied. It was a new 3. Num and input number had nothing to do with each other, except that they happened to have the same value then, right? The same is actually not true here. When I use a new label like this, what it's really saying is that if I want to look and find this function definition, now I can use either this address or my new label, and both will be pointing at the same place in memory. Okay, it's a big difference here. The difference in how we refer to those two is pass by value versus pass by reference. Right? We're referring to the place in memory instead of copying that primitive value. Okay. As we see over here, our functions store a link reference address that is pointing to a location in the heap. We won't get too into that, but our primitive values are stored in a stack, and then objects, arrays, our composite data types, our functions are stored in a heap. Okay. We will not dive too far into how that is implemented. It is a lot of weeds that we can get into there. But taking a look at this new example here that functions can have multiple names, we're going to do the same thing. And I'm going to ask someone other than Odin to lead us through what's taking place here. I want to make sure we get a good understanding of our memory and our thread of execution here. Okay. I do not want to volunteer someone because that's no fun here. Thank you, Brandon.
Hi, Clinks.
Howdy, howdy.
So as of now, we're gonna do the setup. We're gonna have our call stack with we will push the global memory.
Yes.
Sorry, the global execution context inside the call stack. And we will have our thread of our TOE thread of execution inside the global execution context. And we're gonna start with line 1. We're gonna declare a function label multiply by 2, and we're gonna store multiply by 2 in the global memory, assign it to a function definition, and we're going to declare a constant variable label output, assign it to the evaluated result of multiply by 2, passing in the argument 9. At this point, we will open a local execution context with a global memory. And we're gonna whip in the thread of execution into the local execution context. And we're gonna push our multiply by 2 into the call stack.
Yes.
Now we're gonna pair our parameters with our argument, which it will be input number will be assigned to 9. And we're gonna declare a constant variable label result assigned to the evaluated result of input number times 2, which it will be 9 times 2, 18. And we will return this result. And this result will be returned into the global memory. So output will be assigned to 18.
Okay.
And the local execution context will be eligible for garbage collection.
Absolutely.
And we will pop off multiply by 2 from the call stack. And we will weave in our thread of execution into the global execution context.
Lovely. Keep it going.
Now we're gonna declare a constant variable label, new label for multiply by 2, assign it to the function definition of multiply by 2. I think that's how you say it. And then we're gonna declare.
I'm gonna pause you real quick.
Yeah.
You're right. We are pointing at that function definition. What did we just talk about? Is it going to be the same function definition, or is it going to be a copied function definition?
It's gonna be a copy.
Is it? Why do you say?
For what I understood, for what you said, it was like it's gonna be only one function definition, and new label for multiply by 2 will have access to that.
Yes.
Function definition. So I don't know how to call that.
Maybe a way to think about it here is that we're pointing at that initial definition. So maybe I have two contacts in my phone that are actually the same phone number. Might be a way to think about it. Same location, same address. We just got two labels for it now.
Okay. So if I were to say it, how would I say that? If I were to technically communicate that?
Yeah, we have provided, I mean, it's aptly named. We have a new label. We have a new label for that function definition. So now we have a new label that is pointing at that same reference in memory, that same place in memory.
Okay, label for that function multiplied by 2. Okay. Should I continue?
Yeah.
Now we're gonna declare a constant variable, label fresh output, assign it to the evaluated result of invoking new label for multiply by 2, passing in the argument 10. Now we're gonna create a new local execution context, a new global memory. We're gonna weave in our thread of execution into the new local execution context. We're gonna push our new label for multiply by 2 into the call stack. We also have our local memory, and we're gonna pair our parameters and arguments. Input number will be assigned to 10. We're gonna declare a constant variable label result, assign it to the evaluated result of input that number times 2, which will be 20. And we're gonna return the result into the global memory. So fresh output will be assigned to 20. This local execution context will be eligible for garbage collection. We will weave out our thread of execution into the global execution context, and we'll pop off new label from multiply by 2 out of the call stack. And I think as of now, we're done.
What was the one last step I had to bring up last time?
The global execution context will be eligible for garbage collection.
Absolutely. That doesn't matter what color I use. Yes. Right. Awesome. Thank you so much, Brandon. So we just labeled the same place in memory so that we could refer to it with two different labels here. Yes, Faye.
Oh, actually, for my last sentence, I already got my answer. My question was, the function definition, it has a new label, right? So the original label is still working?
Yes, the original label is still working.
Yeah, that was my question, so thank you.
Absolutely. That's a good question to have and a good one to answer. Thank you for sharing. Any other questions about this concept? We got two ways of accessing that function definition now. Interesting, interesting, interesting. Okay, let's keep it moving. And actually, let's take a quick 5-minute break. Need to use the bathroom. I know we've been together about an hour now. We'll come back in about 5 minutes. Before we hop into our closure here, I'll just stick around. So if you have any other questions, maybe about what we've covered so far, or I'll just answer any questions, that's fine too. But we will start slides up again in 5 minutes. Yes, Matt.
Yeah, hi. Yeah, the part that I missed was, so I know that it goes on the call stack and it opens a local execution context when you make the call, but but the global execution is always there, right? And local opens and then it closes. That global is always like throughout the life of it.
Yeah, throughout the life of the file, the module, whatever it is that we're working within.
Thank you.
Yeah.
Could we talk a little bit more about garbage collection? I feel like for me, it's a little bit of a, I mean, I know what it is, but it's still kind of foreign. Like I wish I knew more. If you have like maybe just a little just summary of like, I know we're always collecting like stuff that we don't need to use anymore in the toe or like in the whole code. So is that pretty much it, or is there more?
That is a lot of it. As it relates to these local execution contexts, and this will help relate to our closure a bit later, there's no way for us, maybe in this example here, there's no way for us to call upon result outside of that specific invocation, right? If I tried to, at the end here, console log result, I'm not going to get anything. And so because there are these things that exist in our memory somewhere, they're taking up space, but we have absolutely no way to access them. We back up, get them ready to send them to the curb and you know, picked up by the garbage collectors.
That makes sense. Is there ever a time where like you would ever want to console.log that result or something like, or not garbage collect, or does it do it automatically? Like
JavaScript's going to do it automatically.
Yeah.
The nice thing about JavaScript, in some other languages, it is not always as simply automated a process. So for now, as you're working with JavaScript, understand that if we lose the ability to reference something, thank goodness JavaScript is going to garbage collect it for us.
Okay, awesome. Thank you. That was my question. That was really good.
Yeah. Thanks. Yeah, Matt.
Yeah, in your last answer on the garbage collection, you made me think of another question, and that is that the reason why you use those labels for the heap? Because is it because you want to control what you have in memory, or can you still control them with the other type, the value?
So
it has nothing to do with that.
It does have something to do with that, absolutely.
Okay.
If I no longer had a label that referred to a function or an object or an array, then that would need to be garbage collected. The process of storing things in a stack, which is what I would do for a number, what I would do for a string there, what I would do for a Boolean, amongst the rest of our primitive data types there, that is stored in a nice little stack, okay? And there are limits on the amount of information that can be stored in that stack, okay? If anyone's ever played a video game where it had like maybe a maximum gold value, for me, I played RuneScape for the longest time, and the limit was 2.147 billion gold coins that you could have. The reason for that is because it was a primitive value that was being stored in this stack, whereas objects, functions, which I do not want to get into this, but functions in JavaScript are objects. That's frustrating. Please don't think about it. It makes my head hurt when I think about it too much. Those are stored in a separate heap, and I don't have as great a shape for that. That kind of answered the question. It's a difficult one to get a full answer on without making a new lecture.
Yeah, that gives some insight. I mean, till now I didn't realize that like it was so small for those variables, like the stack ones. I didn't realize that there's some limitations there.
And it's not necessarily terribly small. And the reason that we do a lot of object-oriented programming is so that we can take advantage of these heaps. But even within those heaps, we have stacks for the primitive values. And so we get back into that again. But okay, I think we're back at time here. Maybe took an extra minute. That's okay. Maybe it took someone an extra minute to get some more coffee or go to the bathroom. But we will get started again here. Okay. So far, as we followed our thread of execution and we've entered into these local execution contexts, as we called upon these functions, we've invoked them, get their own little environment, that nice little box that we're making there, right? We've created this nice live store of data, right? Our local memory, that variable environment, that local execution context, right? It's specific to that invocation, right? Result didn't exist outside of an invocation here, right? Created those special little contained environments so that when that function did finish executing, that local memory prepped for garbage collection and picked up by the garbage man, right? But what if we could hold on to some of that information? That might be useful, right? Might be good to know if something has been called before. Might be good to know how many times something has been called. Might be good to know if something's been called with a particular argument before. Maybe we might be able to use the concept that this hard parts is all about to do that, right? We want to be able to let our function definitions have an associated cache or some persistent memory that isn't so greedily being picked up by the garbage collector, right? But that's all going to start with us returning a function from another function. This is going to feel weird at first. That's okay. So functions can be returned from other functions in JavaScript. Okay. So here we see create function, right? The label create function, the definition of it within, again, we see multiply by 2, right? Where if we provide a number to that multiply by 2, we return that number times 2, right? That's going to be our evaluated result of invoking that particular function. But here we see returning, that is an eraser, returning the label. So if I call upon create function, the evaluated result is going to be the label multiplied by 2. Okay. So when I'm defining a function, I get a label and then I have a definition that's associated with that label, right? And that definition is saved into memory somewhere, and the label is my way of accessing that place in memory, right? So normally, if we don't have some way of referring to that label, continuing to refer to that address, that reference in memory, it's going to get garbage collected, right? If I can't access it by any means, there's no point in it continuing to hold space in my memory. But here we're going to start to see a way that we can hold on to that reference point. Okay. Let's walk through this one here. Who wants to help me out? Yes, is it say to?
It's set to, yeah.
Set to, okay. All right, get us started here.
So first we're going to declare a function to the global, we're going to push global memory to the call stack.
Yes, our global execution context here. Awesome.
And then we're going to declare a function to the global memory called create function. And then we're going to declare constant generated function or func to be the invocation of create function.
Absolutely. So now we need to figure out, what does that mean?
So now we're going to push create function to the call stack and open up a local execution context.
Absolutely. My toe is dipping on into that local execution context. And then local memory, sorry.
No worries. And then in local memory, we're going to declare another function multiplied by 2. And then here, would we assign? No, we wouldn't assign anything. We would need to, we would run the function, correct? So we would return.
So what does it look like when I call upon or run a function? What do I need to see behind the label or after the label?
The parentheses.
You did see the parentheses, right?
Yes.
So are we going to run a function inside of create function?
No, we wouldn't.
No, right.
Okay. So then we would just return multiply by 2.
Absolutely.
Okay. And we would garbage collect this and return it out to the global memory.
Okay. So here's where we get fun, right? Our context, right? We're done here. But what is genfunc now going to be pointing at? Generated func.
Multiply by 2.
Yeah. So interestingly enough, from here, when that was defined and a place in memory was created, now genfunc is going to be pointing there. And as a result, we have a function definition that's there. Okay. But it's pointing at the place in memory that was created when we ran this create func. Interesting. Keep going.
Okay, so then from here, since we returned it out, would we also pop off the create function from the call stack?
Yes, we would.
Okay, perfect. And then we would go back to the global memory and declare result as generated func.
Okay. We would declare result as, we declare it as generated func, or what would we be assigning there?
It would be a function, correct?
Yes, the invocation.
Invocation of a function.
Yeah.
Thank you.
And I'm going to go back just real quick. This is my bad in kind of defining this sort of label pointer here. If I try to call upon multiply by 2, let's say down here, is that going to work?
No, because it's garbage collected, correct?
This label is garbage collected, yes. I will not be able to call upon multiply by 2, the function that was initially defined with that label. I will not be able to use multiply by 2 in order to access it.
Okay.
I needed to go back and mention that. That's on me. Keep it going.
No, I was actually going to ask you if we also
Perfect.
Yeah. Okay. So then result would be that function, correct?
The invocation of that function.
Invocation of the function. And then we would push it onto the call stack.
Mm-hmm. So, genfunc.
And we would open up a local execution context.
Yes, we would. And our toe moves on in here.
And then in our local memory, we would declare num to be 3.
Yeah, we would assign that value to that parameter.
And from there, we would return out num, which is 3 plus 2, which is 5.
3 times 2, but you got
Oh,
the
oopsies.
programming aspect of it, which is the important part. So we return
6.
absolutely.
And that would go out to the global memory, and we would garbage collect this local execution context and pop it off the call stack.
Absolutely. And so then where did that get returned out to?
Global memory as a result.
There we go. Looks like Christmas here with this red and green. What's the last bit that happens?
We're going to garbage collect the global execution context.
Here are. Goodbye. We finished our file. We didn't do anything else with the results. We didn't save it into a database. We didn't send it to another file. There's nothing being exported here. And so we don't want it to continue taking up place in our memory. Awesome. Thank you so much.
Thank you.
I saw some puzzled faces here, so I'm hoping that means we've got some puzzling questions. If it takes a little longer to figure out what the exact question is, that's okay. We got plenty of time. Okay. So we can return a function from another function. And that's not just we can return the evaluated result of an inner function or another function. We can return that label, right? And so even though this was defined inside of this local execution context, right? And was initially only available within that local memory, right? Because I'm returning out that address, that reference point, my pointer in order to access this definition here, I'm able to maintain a reference, a way to access this definition, and so we do not lose it. I get thumbs. You might not know what that means. Thumbs up if we're good, 70%. If we got a little bit of a question, sideways, we've got a fair amount of question. Thumbs down, you want to come here again with a different instructor. Yes, Matt.
But that section, it was garbage collected later on, right?
Yes, eventually it was. Yeah. When we get to the end of the file and we no longer have anything else that is referencing that place in memory, we're not saving it anywhere else, then it is eventually. But it escaped. Escape might not be the right word here. We were able to continue referencing it outside of that local execution context where it would otherwise be trapped and garbage collected on its own there. Yes, Faye.
Oh, why don't we directly assign multiply by 2 to the label generator func? What's the difference between directly assign the multiply by 2 to generate func and use the create a function to return? Do you got? I mean, we can directly assign multiply by 2 to the generator func, right?
So you saying on out here, let me make sure I'm understanding this correct. If after I have done this line, if I then said multiply by 2 equals gen func, is that what you're asking?
Yeah, what's the difference between them?
That I would just be I would be creating a new label that now does exist in my global memory and using that to reference that place in memory.
So if we use call the function create a function, then we do not need multiply by 2 in the global memory. I mean, if we can directly assign the generator func, that the function definition or multiply by 2, why do we, do a lot of work to?
Why do we do a lot of work? So that I can demonstrate closure coming up here. That is, this is not a practical implementation of something that you should do in order to multiply something by 2, by any means. This is so we can demonstrate the concept of being able to do something like this.
Okay, I'm just confused why do a lot of work.
For sure. Oh, absolutely.
Okay, thank you.
Yeah. That is the unfortunate part about instruction, is that oftentimes we have to use examples that have to be simpler so that we don't have to define all of the other things that are taking place in order to explain just this specific concept. Because we could go through some node packages here, but there'd be way more questions about other syntax and implementation that would defy the purpose of teaching about closure.
Okay, thank you.
No, it is, this is not something you should write if you want to multiply things by 2. Absolutely. Yes, Brandon.
Hi, thanks. In the last line, when you invoke generate func, we're directly going to the local execution of multiply by 2, right?
On the last line, when I call upon generated func, what I'm going to do is I'm going to multiply 2 does not exist anymore. That label does not exist anymore. I want to make that clear.
Okay.
Generated func is now pointing at that definition in the same place of memory, where at one point we could use multiply by 2 to refer to it, but now we have to use gen func in order to refer to that place in memory. Does that answer question or bring up more question?
I think you answered the question. Okay. Yeah, thank you.
Yeah. Yes, one last question here.
My question is, what if I console log the generated func? What will I get?
If you console log generated func either here or here, let's say, you will see that function object. So you will see what is contained within this definition and all of the other properties.
Within the bracket, within the curly bracket?
Yeah.
Okay, got it. Thanks.
All right, let's keep it going. Okay. So now we're going to call a function in the same function call that it was defined in. Okay, we're getting weirder. All right. Here we see this function outer, and we've declared a counter, and we make this increment counter function. Looks like it's going to increment the counter. It looks like it's aptly named. And we're going to call upon that increment counter function, and then call upon this outer function here. So where we define this function determines which of these variables, so we've demonstrated before, right? Depending on which context, which memory we have access to at that point, that determines what we have access to when we do call upon that function. Okay. All right, we're going to walk through this one. Get a new person again, and if you feel like you can't do it, I bet you can. We've done it 3 times now, and it is just walking through the same. Here we go. Yes, Jordan.
All right. We've got our global execution context.
Oh, yes.
We need to draw our thread of execution and put the global stack frame onto the call stack. First thing we're going to do is declare a function outer. That'll be assigned a function definition. And then we invoke outer. So we'll create a new local execution context. We'll thread our weave our thread of execution into that execution context, and we'll push the outer stack frame onto the call stack.
Sure will.
We don't have any parameters and arguments to pair here, so we can declare a variable counter and assign it 0. And then we declare a function increment counter, and we'll assign that a function definition. And then we will we'll invoke increment counter. So that will open a new local execution context. We'll weave the thread of execution into that execution context, and we'll push the increment counter stack frame onto the call stack.
Absolutely will. And our toe moves on in here.
And then within this execution context, we will increment counter by 1. So I think I'm actually not sure what happens with counter here. We're not returning anything from increment counter. I'm not sure if the value of counter in local memory changes actually.
Okay.
In the outer execution context.
So we know that we can't go outside in, right? From our previous example, I could not call upon multiply by 2 from the outside in that global execution context, access that was in that local. In the opposite direction, what do you think?
I think values can move like down the call stack.
Yeah, I specifically draw it in this way as if they're within one another, because the first place that it is going to look is its own local memory here, of course. Right? It does not find a counter that has been declared within this specific execution context, within this specific local memory. And so this does exist within the other local execution context. And so we look there next. And what do we find?
We find counter.
We do find counter. What do you think is going to happen to counter?
Incremented by 1.
It absolutely is going to be incremented by 1.
Reassign the value of 1.
Okay. So counter is now assigned the value of 1. Now what?
We're finished in this increment counter execution context. So we didn't hit a return keyword, but we're done. So I guess it's eligible for garbage collection. We'll weave the thread of execution back out, and we'll pop increment counter off of the call stack. We're also done in the outer execution context. So that execution context becomes eligible for garbage collection.
Sure does.
We'll weave that thread of execution back out into the global execution context and pop outer off of the call stack. And now we're also finished in the global execution context. So that becomes eligible for garbage collection as well.
All the X's. So we can call the function within another function where it is being defined and have access to that variable counter that, while not within this increment counter function, is on that same level, right? On that same level or farther out, we have access to that counter label and value there. Okay. So inside out, not going to work. Outside in, we can continue looking for it. Yes, question?
So counter wouldn't go, why does counter not go into the local memory of increment counter?
What do you think?
I'm not sure, because how I understood it was that it is stored in there because it is like a closure technically, but it wouldn't go into the local memory.
So it's going to remain in this local memory, right? Because that's where it was initially declared, and we didn't have that's where it was initially declared, and that's where we're acting upon it, and we didn't have it otherwise declared within here and have it changed there and have sort of an immutable data type that we're dealing with. I'm getting into the weeds here, but because it was initially declared here and we can go inside out, it's not going to change from being located at this place in local memory. It's still going to be accessible within here. If it moved inside, now my red box, my outer invocation, no longer would have access to counter, right? Which is not.
Okay, and you can store like as many variables as you want like that, right? Okay.
Mm-hmm.
Got it. Thank you.
Yeah. So functions can have access to variables that are outside of them, right? On the same level even. They don't have to necessarily be inside of that function, right? Even if they're inside of this other function and they're both, hanging out on that same level there, right? Doesn't involve bringing it into its own local memory, right? We looked there, we didn't find it. And so we looked one level outside of that and did find it. Getting very close to closure here. All right. Here we go. Calling a function outside of the function call in which it was defined. Okay. So here we see something very similar, right? But instead of invoking increment counter inside of outer, we return that label, right? And when we returned the label earlier, right, that multiply by 2 label assigned it to our generated func, that meant that we then still had access to that place in memory, right? Hold on to that. We're going to walk through this one, see what happens. I need another brave volunteer. You've seen 95% of this done 4 times now. And I'll help you if there's any percent of that you need me to help you with. So, yes. Thank you for volunteering. Is it Yating?
Yes.
Nice. All right. Help me out here. What's happening?
So first we're pushing the global stack frame onto the call stack.
Yes, we are.
And the thread of execution weaves into global execution context.
Mm-hmm.
And we're declaring a function with the label outer.
Yes.
In global memory, and we assign it to a function definition.
Mm-hmm.
And then we are declaring a constant with the label of my new function.
Okay.
And we assign it the evaluated result of invoking outer.
Awesome. Now we
And
got to figure out what that means.
yeah, so we're opening a local execution context and pushing outer onto the stack call stack.
Y'all are doing so great with saying push every time. I usually have to remind people that it's push way more often than this.
I have to remind myself too. Yeah, and the thread of execution weaves its way into the local execution context.
Sure does.
And in the local memory, we're declaring a variable with the label of counter, and we assign it to the value of 0. And we're declaring another function called increment counter, and we assign it to a function definition. And then we are returning increment counter back to where it was called, which is my new function.
Mm-hmm.
And the local execution context is ready for garbage collection.
Sure is. Just a reminder there, we're pointing at that same place in memory.
Mm-hmm. So we pop the outer of the call stack. And then we're calling my new function. So we're pushing my new function onto the call stack. And we're opening another local execution context.
Someone may have already noticed that I haven't done something that maybe I've done before. Interesting. Keep it going, sorry.
Yeah, so we are incrementing counter by 1.
Mm-hmm.
So counter becomes 1 in the local memory.
Okay. My new function. Yeah, where is counter right now?
It's under my new function.
Kinda, yeah. We'll put it there for now. So counter,
Mm-hmm.
it's gonna increment. So counter changes to 1.
And I guess we're ready for the local execution is ready for garbage collection.
Mm-hmm.
And my new function, we pop that off the call stack, my new function. And we're calling my new function again.
Yeah.
So we're opening another local execution context, and we're pushing that onto the call stack again.
I'm gonna make this one very small because it's gonna look remarkably similar to the one that we just did.
And it's incrementing counter by 1. So counter becomes 2.
We go back out into our global, then we head back in here.
I'm not sure where a counter is returned.
Where is it? Yeah, where is it at? Let's find out soon.
I'm guessing it's under my new function. Like they bundled up.
Yeah, you would be right. Thank you so much. You did a great job.
Thank you.
You're right. counter is going to become 1, and then counter is going to become 2. And that's really weird, right? So when I returned this reference point, right? I returned that reference point. I didn't lose counter. Counter kept incrementing. I had access to it when I called upon it outside of this outer, right? I invoked outer once, but counter wasn't inside of increment counter, and an increment counter was what was returned there. This is not intuitive. This is okay if this is a brain exploding, confusing moment. Okay. When we returned that function label, right, that reference to that place in memory, we also brought with it all of the surrounding memory that is attached to that function. Okay. We look back here, right? We were able to increment counter with that increment counter function, even though it was outside of the local execution context that was being created there, right? It was on a higher level there, it was on the same level within outer. Again, that's true here, right? But in a weird new way, right? When we invoked outer, we returned that reference to increment counter, reference to that point in memory where that function definition was located. And that function definition requires us to increment that counter, that variable that's associated with that function and acted upon within that function. Okay. Now we have access to that data that doesn't go away even when this local execution context and this local execution context and this local execution context is garbage collected. Okay. Our wonderful volunteer very aptly described that it is now bundled with my new function. Okay. Yes, question.
So suppose we have another variable like just below the counter, like let num equals 3. When we return the function increment counter, will the variable num return come with the function?
This is the really frustrating part. Sort of.
Because inside the increment counter function, we need the variable counter, right? But if we don't use the variable num, so num still come back together with the function?
We would have no way of accessing it or acting upon it, but it would be there. And when I say no way, I mean no safe way, no way that we would ever implement, no way that we would ever think to use here. There's one very, very weird way to do it, but it is not one, it is one that all documentation recommends against because it is crazy security vulnerabilities defying. The same is true for counter, that we can act upon it and we can see that value continue to increase. Like, let's say if we did have a console log that existed within here of counter, so that every time we did call upon my new function, we would see counter continue to increment. But if I try to say my new function dot counter, or if I try to reference counter anywhere else, I'm not going to have any luck. But it's there, and I can act upon it.
My question was, if when we return the increment counter with counter equals 0 and another variable like num equals
Right.
3, if the num equals 3 also can be returned to the global memory.
Yes, but again, we have no way of accessing it. Or
how about later we write another function, use num?
Within outer,
like below the my new function, we write another function, use num.
Console log num, let's just say.
Yeah.
It's not going to know what to do with it. It's not going to be able to find it.
Also, it's still inside the function.
If we did it inside of increment counter, yes, we would see 3.
But we console log num, we cannot see.
If
3.
we do it in our global execution context, instead of including it within this increment counter definition, apologies, my drawing is very messy at this point. If we try to reference it anywhere else other than within increment counter, as this is written, we will not be able to access that new variable num.
Okay, thank you.
Yeah. Yes, Jordan.
So as I understand it, the variable counter right now, it exists within the closure attached to the function definition of my new function.
Yes.
So we can't access counter at like outside of calling my new function. Okay, so like within this, short snippet of code that we have right here, we can increment counter, but we can't actually we can't log it or anything like that, right? Because it's not in that function definition. Okay.
Yes, Stephanie.
My new function is pointing to the function definition. Is that function definition and counter stored in local memory, or at this point, is it now stored in global memory?
It is global.
Okay.
When we talk about what is genuinely stored in each of these local memories versus global, the label is what's being stored here. And when we lose the label, we no longer can access it in any memory.
Okay.
That's the little differentiation I want to make, is that because now we do have a label of my new function that is pointing at that place in memory that was created within that other local execution context, we now have a label that exists in global memory that allows us to access that address, that reference, that space in our overall memory.
Okay.
Okay, we're going to talk a little bit more about what is being implemented here. This is our bond, this is our closure, this is our backpack, whatever you'd like to call it. Okay. When a function is defined, it gets this bond to the surrounding local memory, like we saw there with our counter, like we would see with that num variable that we were talking about. Even if it wasn't utilized, it technically would exist inside of that scope there, which is really weird. Okay, it's our variable environment where it's been defined. Okay, when we returned that function, we brought with it all of the surrounding memory that was attached on that function, attached inside of that variable environment. Okay. And so if we're utilizing it, if we do something else with this counter, if we did return the counter maybe from this inner function, then we can still utilize that, right? That data doesn't go away when that local execution context is garbage collected. This is our persistent data. This is what makes modules possible. This is what allows us to transfer state between different files, between different modules, put together real modern applications, right? so that we don't end up with one giant file that we're dealing with. Okay. This is where we build that persistence. Okay. So when we saved counter and increment counter, pulling those out with my new function like that, we made a link under the hood from that function, that increment counter, to those surrounding properties through this hidden property, right? So I'm talking about, there's not a way that we're going to access this. This is not something that you ever need to worry about doing. It's not something that you're ever going to want to do because it is an incredibly unsafe thing to do, right? It's attached with local memory to that function, the property called scope inside of 2 square brackets. Okay. It's a scope link that's taking place there. That is not as important as just understanding that through closure, we can have that link between these variables and a function in this variable environment. Okay. This is weird. It is. Right? We walked through that first part and we said, hey, you can't access anything from those local contexts, right? Can if it's closured or backpacked on there. Now, if you tell someone outside of Codesmith that something is being stored in a backpack, they probably will not know what you're talking about. So do refer to it as a closure. But a backpack is a great way to think about it, right? It's going to move around with that function. It's attached to it. It's not going to move anywhere. It's not got something that's going to keep it going unless it's attached to something, unless it's backpacked onto it. Okay. When increment counter is defined inside outer, it gets a bond to that surrounding local memory. We return that function definition, that pointer to that function definition out of outer into our global, give it that new name, my function, right? But that bond is maintained. It gets returned out, attached onto the back of that function definition. So our local memory now stored attached to that function definition, even though that outer execution context, that outer local execution context is gone. Okay. So when we run my new function, it's first going to look in its own local memory for any data that it needs, as we'd expect, and then look inside of the backpack that's connected to it. So it'll look and see, hey, do I declare counter inside of myself? No, I don't. So where is it? The next place it looks is its own backpack. Its own closure. Some other terms that we can use to refer to this backpack is the closed over variable environment, or COVE, the persistent lexical scope reference data, PLSRD, or backpack, or what most people will understand what you're talking about when you refer to it, closure. There are experienced software engineers, folks who've been in the industry for several years, who still do not have a full grasp on how closure works. If you are sitting here and this is confusing, you are not alone, not just in people who are learning software engineering, but folks who've been implementing it for several years. This is weird. It defies some of our original understanding of how these lexical scopes work, right? So our live data, that closure, connected to increment counter through that hidden property of scope. You will not access it. Just know it's there and that is how you are able to access it, okay? And it persists when that inner function is returned out. This is going to beg some new interesting questions, though. What if we run outer again? I'm going to need the bravest soul to lead us through what might be happening here. It's again going to be 95% of what we've done, and then a little bit of 50-50 at the end here. But we're here to learn, so that's okay. At Codesmith, in every pair programming session, you're going to have to do something like this. You have to do group presentations. Jordan, did you lead us through one of ours already? You did. I really appreciate you volunteering again. I'm going to force someone else to.
I just couldn't sit with the silence.
I really appreciate that. I'm too used to it at this point. I taught at one point to maybe 30 black cameras, not at Codesmith. So I can handle a little awkward silence. But Faye is going to save us.
Okay. In the code stack, we first post on global context, execute context. And then in the global memory, we declare a function labeled outer, and we assign it the function definition. And then we declare another variable labeled my new function. We initialize it with the evaluated results of calling outer. Then we push outer on the code stack and open up a new local execution context. And then I will thread dive in. Then in the local memory, we declare a variable called counter, and we assign number 0 to it. Then in the local memory, we declare a function labeled increment counter and with its function definition. Then we return increment counter. The return value will be assigned to my new function in the global memory. It returns the function definition of increment counter. Then the local execution contexts are eligible for garbage collection, and we pop the outer of the code stack. Then we call my new function. We open up a new local execution context and push the my new function onto the code stack. So then I will thread down in the local memory. We need actually in here we can access counter, right? So we have a counter +1, then the counter will turn to 1.
So it was 0, and now it's going to be 1.
Yes. Then this local memory, local execution context will be eligible for garbage collection, and we pop the my new function of the code stack. Then we call my new function again. First, we push the my new function onto the code stack. And we open up a new local execution context. In the new local execution context, we can still reach out to the counter in the global memory, right? Mm-hmm. So the counter increment by 1. Now the counter will turn to 2. Now the local execution context is eligible for garbage collection. We popped my new function of the call stack. Then in the global memory, we declare another context variable, labeled another function, and we initialized it, the evaluated results of outer. Then we open up a new local execution context. Our thread will dive in. In here, in the local memory, we declare a variable labeled counter, and we assign it number 0. Then we declare a function labeled increment counter and its function definition. Then we returned the function definition of increment counter. The returned value will back to another function in the global memory.
All right, we're going to pause right here. What do we think happens?
So in here, when the function definition back to global memory, the counter come with it will be 0.
Absolutely.
Then we call another function. Oh, no, sorry. The local execution context will be eligible for garbage collection. Then we call another function.
Yes, and apologies. I'm going to get a little bit more drawing done here real quick.
There are too many local execution.
There are a lot of local execution contexts for this particular example.
Yes. So we call another function here. We first push it onto the call stack and open up a new local execution context. In here, it will reach out to the counter. The counter now is equals 0. Now equals 0. So counter plus plus will be equals 1. Okay. Then the local execution context will be eligible for garbage collection, and another function was popped off. It's called stack. Then we call another function again.
I'm not redrawing it.
I like a repeat machine. So yeah, we open up a new local execution context and push it on to the call stack. Now count plus plus will return 2 to the global memory. Then we garbage the local execution context and pop off the another function from the call stack.
And one last step.
My last step, what I missed.
It's the very last step. We reach the end of the file. What happens?
The whole global.
We crumple it all up. Yeah. We're not sending it anywhere else.
Yeah,
Great job. 100% on point. That's exactly what happens. When we call upon outer again, a new function is defined, right? Because increment counter does not exist with that label and has not been defined. It is a new place that is being created when it's defined again, right? This is not, when I call upon it again, saying increment counter is now going to point at the existing place that's in memory. No, we're defining a function again and assigning it the label of increment counter. And so a new place in memory is created. And that means that a new counter is added into that new place in memory's backpack, so that when we get down here, we see 1 and then 2 again if we console logged that counter. They're two separate counters, two separate backpacks. Okay. Because in each invocation of outer, a function is defined. Not just a place is labeled, but a new definition is provided. Individual backpacks here. Because we ran that outer function again. And so a new counter was instantiated within that local execution context. And a new increment counter function was defined. And they were bonded together when we returned that increment counter. And so another new function, I'm erasing, that's okay, had its own backpack and its own place in memory where that function definition was located. Is the syntax that's contained within my new function and the syntax that's contained within another new function identical? Absolutely. But they're located at different places in memory. They have different labels, and they have separate backpacks because they're at separate places in memory.
So you mentioned that if we console log counter, we will not be able to see anything there. So like, I wonder where we will see the change of counter.
Yes, if we ran console log counter down here, we would get undefined, right? We wouldn't see anything. Mm-hmm. If we had it within here, right, within that increment counter, then what we would see is we'd see 1 here, and we'd see 2 here, and then we'd see 1 here, and we'd see 2 here. Because those two counters are separate from one another. They're in their individual backpacks associated with their individual function.
Is it because console log returns value back to global memory?
No, it's because the console log is in the same way if we tried to reference counter anywhere where it did not directly exist in that level of memory or a more outer level of memory, it won't be able to access it. In the same way that if I tried to utilize counter outside of those contexts, I'd be unable to. Same is true for logging to the console. So because counter only exists as it is being utilized by either my new function or this counter only exists in how it's being utilized by another new function, I wouldn't be able to access it in any other way than if it was involved in that increment counter initial definition that is then labeled differently with those two.
Okay, so it kind of like coexists with the function?
Yes, it is backpacked onto there. It's closured onto there.
Okay, all right, thank you.
So a way that we cannot access it would be to look into, let's say, MNFs. This is not how it would look, but this might be a helpful way to think about it. Inside of MNF's scope, inside that property of counter, this is genuinely not a way that you can access it, but maybe a helpful way to think about where it's located. This counter is located inside that scope property. That's the level that you need to understand of of where it's located. It is so deeply embedded into the JavaScript engine that it is something that is inaccessible safely for us as developers. So the only way that we are going to access it, utilize it, is in a way like it is defined here, right? Where we're incrementing it inside of that associated definition. Yes, Faye.
So the another function equals calling the outer function. What if we replace the outer function with the my new function? Replace the.
So if down here I said another function equals
my new function.
Right, just MNF, not invoked, right? No parentheses.
Yeah.
What do you think?
I'm not sure because my new function has been called twice before my new function assigned to another function.
Yeah.
So if we call another function, now the counter equals 3?
Yes. Yes. If we were to just say another function equals that MNF label, then all we'd be doing is applying another label there again. And so they'd be pointing at the same place in memory. And therefore, if I then called upon another function, it would be identical to me calling upon my new function, right? It's just two labels for the same address. And so you're 100% correct. If that were the case, I would see 3 and then 4.
So this my new function is different from another regular function because other function, when we pass it different arguments, it didn't remember last time it was executed, right? But my new function will remember it has been executed before. It will change the argument it remembered.
Yes. If I had MNF here, what I would see in my global memory, or what would exist in my global memory, again, we couldn't see it because this is annoying. I would have my MNF, right, which has my function definition and the cute little counter closure that's connected to it. And if I then said another function is equal to MNF, I would create ANF as a label that would just point at this same location in memory. Cool. Yes, Brandon.
Hi. The question is, when you say this cannot be accessed safely, what do you mean by that?
There is one very, very, very strange way to do it that involves a function that MDN expressly demands you not use. And so I'm not even going to name it. If you want to go out and look on Stack Overflow and find it, it is something you will never use. I honestly did not know it existed because there is no opportunity that you would ever implement it. I know, it's weird.
Yeah, it's like,
I know.
it says we should not, let's say, access it somehow because of some reason. But
Yeah.
The other question was, when you garbage collect the global memory, what happened with the things we did? Where do they go?
Because they are no longer being referenced, there's nothing else after the end of our functionality here. There's nothing that's being exported anywhere else. There's nothing that's being saved into a database. There's nothing that's being used to persist the information that is contained within this file beyond this execution. We do not want it to remain in our machine's memory, right? And so JavaScript garbage collects it for us. They say, hey, you finished this. You did not dictate that this was being saved anywhere else. If you had, we would still garbage collect it in this location because it is now saved somewhere else. But once we reach that end of all of our execution context, we don't want that to just continue hanging around in our memory, right? Otherwise, every time that we executed a JavaScript executable or a JavaScript file or an application on our computer, it would fill up real quick, right? When we get done with that execution context, we do not want that to continue holding space in our memory.
So normally in real life, we will actually, at the end, we'll export it to some database in real life implementation.
Potentially, yeah. Okay. I mean, it depends on the information that we're dealing with there, right?
Thank you.
The closure. I'll come to you right after my summary, Jordan. Closure gives our functions their own individual persistent memories, right? We can utilize modules, we can utilize these packages, import, export, everything, every which way, and not understand this, but it makes it far more difficult for us to have meaningful discussions about those implementations. And that's why we talk about it. That's why we focus in on it, is so we understand why these modules work, why once works, why Memoize works, right? Because it's beyond being a technician who can accomplish a task using these tools, but to be an engineer who can efficiently and intelligently discuss why these tools work, right? In order to implement new, exciting, innovative tools, you can't just know that something does work, right? If we're talking about making innovations, we need to know why these things work, how they work to a certain level. Again, we don't actually want to get so deep in the JavaScript engine that we break all security measures. Okay. So we see this in a lot of different helper functions like once and Memoize. Our iterators and our generators that use lexical scoping and closure under the hood help us achieve our modern, our most contemporary patterns for handling our data in JavaScript. Module pattern, which is so wildly important to us putting together large applications. This is what allows us to preserve state for the life of that application without polluting the entirety of our global namespace, right? Just utilizing these where it is required for that functionality, right? That allows us to have my new function and another new function with their own counter variables that are associated with their specific implementation. And then callbacks and promises. They rely on this closure so that we can persist that state in our asynchronous environments and asynchronous implementations. All right. Yes, Jordan.
Regarding the individual backpacks, I read something on CSX that was very confusing to me, because it seemed to conflict with something that I had heard in another closure workshop. It says, if multiple functions are created in the same execution context and all of them outlive that execution context, those functions each have their own closure, and each of these closures will access the same variables in memory. Therefore, mutation of those variables by one of those functions will affect the other functions in the manner that they will be accessing the same mutated variables.
Yes.
To me, I feel like I'm not understanding that last sentence. To me, that sounds like if outer produced like a function that increments counter and then a function that decrements counter, and you ran them back to back, counter would be equal to 0.
Yes.
Okay.
So what that might look like is I have my outer, my function outer, right? And inside of that, I've got my increment counter. I've got my counter variable, excuse me. And inside of increment, right, I do my counter plus plus, and then additionally, oh, this is messy. That's fine. Fn decrement counter, and here counter minus minus, and then for my return here, I return, let's say, an array with increment and decrement. Like you said, if I then had a variable that was set to outer, maybe I do it this way, outer at the position of 0, and then another that's set to outer at the position of 1 in this array. And I called upon both of those. I call upon the increment one, I see counter goes up to 1. I call upon the decrement one, I see it goes down to 0. Because what's being returned and assigned to outer, oh, excuse me, if I did it this way, outer would be invoked 2 times. That's my mistake. And then we would see 1 and -1. If I instead said const combo, let's say, equals outer's implementation or outer's invocation here, and then I said combo 0 invoked, then I would see 1. And then if I said combo at 1 invoked, then I would see 0 again. So when you start returning multiple definitions that rely on that same variable and you do mutate that variable that is associated with them, it becomes this weird shared backpack situation. Yes.
It makes sense, like
about as much as it can.
In the weird way, yeah. Okay, thank you.
Mm-hmm. What matters in that case is whether or not outer is being invoked once or if it's being invoked multiple times. If it's invoked multiple times, then we have separate backpacks that are being created each time. in the way that we also saw it with my new function and another function, because outer was invoked more than once, individual backpacks were created because the definition was defined more than once, so on and so forth.
In this example, we only invoked outer one time when we declared combo. And
yes.
Then in those invocations, we're just accessing the different elements in that array. Okay, I got it.
Yeah. So because outer was only invoked once, counter was only instantiated once. There's a reason that that's not included in the slides. So if you're sitting here wondering about that question, that's fine. That is totally okay. But that is a way to utilize the same backpack with multiple functions in a weird way. Yes, Yiting.
So what if instead of calling combo at each index, what if we just call combo as a whole, like the whole array? Would it will the counter be 0?
If I just called, based off of what I have written here, if I said const combo equals outer and what's being returned from here is an array, I cannot invoke an array, right? An array is not a function. I cannot invoke an array. And so I would not have any success.
Yes.
That's why I have to pull them out of the individual indexes.
Yeah. Thank you.
That's a good question though. Yeah. Have a good night. Sweet dreams. Hope you enjoyed it.